It is, like I said, it's just trigonometry. Here we got this big triangle, but I was, for some reason, referring to recombination. I should really be referring to T naught. That's showing the size of our current horizon, everything that we can see, and we want that to all, look uniform. And so that means that that scale should have crossed the horizon while inflation was already going on. Yes?
Why is the horizon size constant during inflation? Doesn't the horizon size shrink during inflation and then get bigger?
It's defined to be the Hubble, inverse Hubble.
Oh, I see. It did notation.
Yeah, it's just the inverse Hubble rate during inflation, which is approximately constant. Okay, so we just are looking at this leg of the triangle versus this leg of the triangle and saying the slope has to be 1. And so if you do that, then you get a very simple expression for the number of E-foldings during inflation, solving the equation I wrote down before. You just get Hubble during inflation versus Hubble today, and the reheat scale factor versus the present scale factor, and this is approximately. And the other thing that I have to do to be consistent with this picture, you see I made an assumption here that inflation ended instantaneously and went into radiation domination. So that means that reheating was instant, is as efficient as possible, and therefore the reheat temperature would be equal to the scale of inflation. So I'm setting T reheat equal to the energy scale of inflation when I do this. And under that simplifying assumption, then you get the energy scale of inflation times the temperature today, 2.7 Kelvin, divided by the critical density to the 1/2, and you plug in the numbers and you get 63.6, taking this scale to be at the gut scale. And well, you can see what it would be if it was lower scales. Now what about this assumption? So that's not very realistic, and realistically you would have more gradual reheating, as I've shown here. Inflation would end here, say, and reheating would take some time, as through this perturbative inflaton decay if the decay rate is small enough. And then you can see that when you take that into account, that that actually shortens. So that's going to have two effects. It's going to lower the reheat temperature, as we saw. That formula gives you a lower reheat temperature than this maximum value. And it also reduces the number of E-foldings that you need. It's pushing it from here back to here. So this simple formula doesn't show you that effect. And if you want to see the actual estimate taking into account realistic reheating, then you should look at the paper by Little and Leach. And I'll write down the more accurate formula in a little bit. And so another thing that I missed because we were getting a little rushed at the end here was the whole concept of horizon crossing. So you see these different scales are crossing the inflationary horizon at different times. That's what we usually refer to as horizon crossing, or at least during inflation. There's another horizon crossing that happens later on when these scales re-enter. They recross the red line, so they come back in within the observable universe. That's usually called horizon re-entry, but it's another horizon crossing. And so to define this mathematically, it's easy. Horizon crossing just means that the physical wave number is equal to the, is equal to the Hubble parameter. So K, that's a co-moving wave number. So that's 2 pi over lambda as we see it today. But the physical wavelength is getting stretched by inflation. So this combination and correspondingly, the wave number is going the other way. So this is the physical wave number. It's convenient to refer to co-moving wave numbers when we talk about observations, because then we can just directly relate them to the scales that we measure in the sky. And then, so mathematically, since during inflation, A is e to the minus ht, then we can relate this to the time of horizon crossing, or usually more convenient, we can relate it to a number of E foldings at horizon crossing. Okay, so one other thing I wanted to mention was the relationship between the curvature perturbation and the density perturbation. So there was an argument that the CMB fluctuations could be related rather directly to the curvature perturbation. But for formation of structure, galaxies, we're also interested in the density perturbation, delta rho over rho. And we usually like to Fourier transform it, refer to it in wave number space. And so this turns out to be related to the curvature perturbation by a ratio that is related to horizon crossing. So it's k over h squared times the curvature perturbation. And there's a way to understand where this factor is coming from just from the Poisson equation of Newtonian gravity. That is, del squared of the gravitational potential is equal to rho over 2 m Planck squared. That's what 4 pi g looks like in these units. So that's just the Newtonian gravitational potential. And it turns out that this gravitational potential is approximately equal to minus this curvature potential. And so now you can see where this factor is coming from. In k space, the delta squared becomes a k squared. So what it means is that the density perturbation, unlike the curvature perturbation, which is nearly scale invariant, the density perturbation is not scale invariant. Its power spectrum, it goes like the square of this, goes like k to the 4th. But there is a sense in which it is scale invariant, and that is if you would evaluate this not at a single time, but rather for each scale, if you would evaluate it at the time of horizon crossing, then by definition this factor is equal to 1. So in that sense, you can think of the density perturbation as also arising from a scale invariant spectrum.
Sorry, is that minus r?
Yeah. And well, I'll try to explain why that is in a little bit later in the lecture. Let's see. Now I wanted to answer a question which was asked after the lecture. It's an astute question. And the question was, how come these Kobe measurements go up so steeply at small angles, whereas when you go to L space with the spherical harmonics, you get the power dropping at high L, and high L should correspond to small angles. And well, there's two reasons for that. One is that there's a detailed formula connecting angular space to L space, and in fact, at the bottom of the Kobe original paper, they have that nice formula. And then you can just plug in and you find that things don't go quite as simply as you would guess. It's not like a one-to-one mapping between CL and C of alpha. But the more important reason probably is that Kobe only measured this part of the spectrum. So things are not, this is due to something called silt damping. So you're nowhere close to being able to see that effect in the Kobe data.
So if Kobe only measured that first part, would that rise be equivalent to going up to that first peak?
Yeah, whatever.
As you go up, as you go to that first, into that first peak, and if you're only looking at that first part, then you're going to see a rise.
Yeah, exactly. Yeah, so that would also explain that. Yeah. But I'm not sure because I think Kobe could really only see up to 25, L of 25. So you're not really getting to the rise. Okay. So, as I was mentioning, to actually derive those Doppler peaks, it's a complicated procedure because you have to actually evolve the photons from the surface of last scattering through all the gravitational potential wells that are produced by the curvature and or density fluctuations. When the photon goes through such a potential well, well, you might naively think that whatever energy it loses as it's or whatever energy it loses as it's climbing out, it would have gained as it was going in. But you have to remember that this is all time dependent, and the size of these potential wells is growing at the same time, or the size is growing at the same time as the photons are traversing. And so one needs to take into account all of that. By the way, that's called so this is called the Sox Wolf Effect. The fact that the photons get gravitationally redshifted as they're going through these potential wells. So the fluctuations in the curvature in the curvature get imprinted on the temperature, and it happens in a complicated way. But at least there is a simple, intuitive way to understand why you have these oscillations, and that's because the whole system before. So imagine before recombination, when photons start streaming freely, they're interacting strongly with the baryons. It's a tightly coupled system. And because we have these fluctuations, there's rarefactions and compressions, there are sound waves, there's pressure. So this whole thing is oscillating. And what I've shown in this picture is two different wavelengths. Wavelengths are two different wavelengths of these perturbations, and so the other part of the story is that sorry. So let's see, what's important is at horizon crossing, And so the statement is, see, these things are not oscillating until they cross outside of the horizon. That's when they begin oscillating, right? And yeah, so this is the time between horizon crossing and recombination. So a short wavelength mode crosses the horizon earlier, starts oscillating with a certain amplitude. And then at recombination, that's when it starts streaming freely, and we can see the effects of a photon that was influenced by that perturbation. A longer wavelength one, it doesn't start oscillating until it crosses the horizon a little bit later. It oscillates with about the same amplitude, but you can see because of this time lag, it's out of phase with the other one. And so these sound waves are all out of phase with each other depending on their relative wavelengths. And so that's why when you look in wave number space, you see these peaks and dips in the temperature perturbations. And I'll come back to what's causing this, what's the origin of these perturbations being frozen until horizon crossing. Yeah.
So would you see a peak when at recombination the oscillation is at its amplitude and a dip where it's at its zero crossing?
Something, or the other way around, something like that. I'm sorry, this is rather heuristic, and the actual, whether it's one way or another, that I think that's going to depend on this transfer function and evolution details. So we saw that the power we had an expression for the amplitude of the power spectrum, and it was h squared over phi dot quantity squared. And so what one needs to say to explain why there's, or how the scale dependence is coming in, is that this is evaluated this is evaluated at this scale. This is evaluated at the moment when the scale exits the horizon. So at horizon crossing. And it's the fact that these quantities are evolving with time, which means that, which implies that it's not going to be the same value for all k. So we want to figure out what that is quantitatively. And so we can use the slow roll equation. 3h phi dot is equal to minus d prime of phi to eliminate phi dot in this expression. So we get h squared over, so h cubed over h phi dot. This is going to give us something ignoring powers of m Planck, this is going to give us something going as v to the 3/2 over v prime. And we have to evaluate that at the value of the scalar field corresponding to when. So if we want to know this at a certain k, we need to find the value of phi when that k executed horizon crossing. So that's the horizon crossing of the relevant k. And so we'll see how to do that in an explicit example. But now we can put our formulas together to find out what's the spectral index. Remember, ns minus 1, that was the logarithmic interval, the logarithmic derivative, d log p, d log k. And from our horizon crossing expression, since we have k is equal to h e to the n, right? So log k is equal to log h plus n. And since if we want to do this very exactly, we should also differentiate the Hubble parameter. It's not exactly constant, but usually it's quite a good approximation to ignore that and just say that d log k is dn. So we can write that as d log p with respect to e-foldings. So now let's take now.
Sorry, where is that the k you're interested in? Wait, where is that k equals to h times a?
So this is the horizon crossing criterion.
And by crossing is like the exit.
Exit. Yeah. So this is crossing during inflation. And yes. And so we can say this is the derivative of the logarithm of v cubed over v prime squared with respect to n. And so using the chain rule, these are derivatives with respect to the field. And then we'll have a d phi dn here. Now remember that dn is h dt, so d phi dn, that's phi dot over h. And we also have 3h phi dot is equal to minus v prime. So d phi dn is minus v prime over 3h squared, which is minus m Planck squared times v prime over v. So if you put all that together, you see that these just become the slow roll parameters. And you find that ns minus 1 is equal to minus 6 epsilon plus 2 eta. And of course, this is ignoring higher order in slow roll parameters and also higher order slow roll parameters themselves. There are slow roll parameters corresponding to higher derivatives of the potential that we're ignoring. Okay, so that's how to take the number that's measured by Planck and pit it against your inflationary model of interest. But in addition to the spectral index, there's also the amplitude of the power. So it turns out, so the amplitude of the scalar power spectrum, we derived what it was parametrically, if you look more carefully, there's factors of 2 pi. Sorry. And so you can write this as v over 24 pi squared m Planck to the 4th with the epsilon slow roll parameter in the denominator. Now, of course, this is a scale-dependent quantity, and so one has to specify it at some scale, and Planck chooses, and that scale is denoted by k star. Planck chooses k star to be 1 over 20 megaparsecs. And at that scale, they find that the value corresponding to the overall size of the Doppler peaks is, they like to write it as e to the 3.1 times 10 to the minus 10 for some reason. Now, if we write out, again, what's epsilon, then we can relate this more directly to parameters of the potential. So it implies that v to the 3/2 over m Planck cubed v prime is 5.1 times 10 to the minus 4. So this is the other thing you need to impose if you're putting an inflationary model, pitting it against the data. And what you see here is that this is going to have some impact on the overall scale of the potential. Whereas the slow roll parameters themselves, they don't care about the overall scale of the potential. They're always v prime over, let's see. Yeah, they're always v prime over v squared or v double prime over v. So overall changes in the overall scale have no effect on the shape of the potential. It's only the amplitude that cares about that. Okay, now so far we've just been talking about scalar perturbations, but there's also gravity waves, and those are known as tensor perturbations. The graviton also gets excited during inflation, and again we'll come to this in a little bit, how these quantum fluctuations arise. But I'm just going to tell you what the effect is first. And these are also, so the gravity waves, we don't see gravity waves directly from inflation. LIGO looks for them, but that's not yet observed. However, the gravity waves also cause, they give a contribution to the Sox Wolf effect, because the gravity waves, they correspond to a gravitational potential. So long enough wavelength gravity waves give a contribution to the temperature fluctuations. And it's a contribution which is only existing in this region because for higher L, those wavelengths are getting redshifted after recombination. And so their effects are dying off. So what you find is that the tensors are going to give some shift to the height of this if they're in a significant way, but then they're dying off here, so it's only this region that's being affected. But it's calculable, and that gives you a constraint on the tensor power spectrum. And I'll just write down the form or the result for the tensor power spectrum. It's like the scalar one. It goes like h squared, and that's just because the amplitude of the quantum fluctuation of the tensor, it goes like the Hubble parameter. But it doesn't have the 1 over epsilon. And remember that 1 over epsilon, that was ultimately coming from this picture where different scales, this picture, where different scales of the scalar field were ending different places were ending inflation at different times. That's not an issue for gravity waves. And similarly to the scalar spectrum, it's parametrized in just the same way, but it has its own spectral index, which one can compute in slow roll inflation. And it has its own amplitude. And well, we see what the amplitude here is, and we can compare. So we can compare to the scalar contribution to get a ratio, tensor to scalar ratio. R, so that's AT over AS. And if you just compare these two formulas, it turns out to simply be 16 times epsilon. So that gives a constraint on epsilon, and the current constraint from Planck is it's less than about 0.1. But for some reason, they choose a different reference scale for the tensors. I guess the reason they do that is because it's sitting down there at lower wave numbers. So they use 1 over 500 megaparsecs to normalize that. Now, this has a very interesting consequence because of the fact that it doesn't depend on the shape of the potential, but only on the magnitude. So h squared, that only cares about the actual magnitude of the potential. This puts a limit on the scale of inflation evaluated at this reference wavelength. That so V star to the 1/4, that's the energy scale of inflation, has to be less than 2 times 10 to the 16 GeV. So that's very interesting that we already know inflation can't be all the way at the Planck scale, or at least not at the time of this horizon crossing. If we go back in time, in this picture, of course, inflation could have lasted arbitrarily long before it starts to become observable in the cosmic microwave background. And by the way, of the nominal 60E foldings, those CMB fluctuations only correspond to about 8 that we can see through the CMB. But there could have been arbitrarily much more inflation earlier on, and the scale of inflation, it could have been much higher early on, and maybe it came down to this level. But it's in this region where we know that value.
Lower modes in the power spectrum, in the temperature power spectrum, but under low modes limited by statistics or cosmic variance. So do you still end up getting precise boundaries?
Well, I suppose that limits how good the bound is, but that's of course taken into account in the analysis. Yeah, so there's cosmic variance. That's why you see those big error bars in the predictions. Yeah.
Do you know, like, are there bounds equivalent for like smaller wavelengths? Because presumably that's going to like push further and further back. So like this is only for one scale. But I would like to know like what my bound on inflation is, like as far back as I can go.
I think this is the best you can do because we already know that it's almost scale invariant. So looking at different scales is not going to, I think they probably choose this one in order to optimize to get the best bound that they can. So one other thing before I show what these constraints look like, I also just want to mention briefly polarization. We don't really have time to go into any details, but you probably know that Planck measures not only the magnitude of the temperature fluctuations, but also their polarization. And so there's two complementary directions of polarization. There's the ones where the electric field lines are pointing radially out from some fluctuation. And then there's the B modes, which are the circulating ones that have a curl. And one can understand that these are caused by the fluctuations in the density itself. So these are due to the scalar perturbations, whereas these are only caused, well, they're caused by foreground emissions like dust, so that makes it difficult. But in terms of their inflationary contributions, these are only sourced by the tensor, the gravity waves fluctuations. And so these are a holy grail for CMB physics, because if one could unambiguously observe those, then you would say we did see the scale, or we did see the tensor contributions, and therefore we know that inflation happened at a pretty high scale, and now we've learned something pretty definite about inflation. And of course, a few years ago, there was huge excitement because BICEP 2 collaboration claimed that they did that, but now it's agreed that they were just seeing spinning dust in the galaxy foreground. But this is observed. So so Planck gets extra information by looking at the E-mode polarization.
Is there a lower bound on the scale?
Well, you would like it to be above Big Bang nucleosynthesis, and you would probably like it to be above electroweak scale, because I think there's not many good mechanisms for creating a baryon asymmetry below that scale. That would be my personal lower limit for the scale of inflation. But certainly MEV scale, that you can't mess with that. So this is the nice result that no doubt you've seen many times before, that's combining constraints on the tilt of the spectral tilt versus this tensor to scalar ratio. And here is the central value that I quoted for n sub s, and well, around here is the 0.1 limit. And the various ellipses here are what you get from, you see, you get less constraining power if you only look at the temperature fluctuations by themselves. But if you look at temperature combined with this E-mode polarization, then you get stronger constraints. And so now it'll be interesting to see how the model predictions fit onto this picture. And I think that's what I want to get into next. So what I'd like to do is work through an example which is known as chaotic inflation. It was one of the early models of new inflation, well, around the same time as people came up with new inflation. Andre Linde proposed a very simple class of inflationary models that are known as chaotic. And they're nothing more but a monomial. And so one could very generally parameterize them as a dimensionless coupling times Planck mass to the fourth, and then the ratio phi over mp to some power where we need p to be greater to 0 to get inflation. And so if you plug that into the Hubble parameter, then that's root lambda over root 3. We just get 1 power of m Planck, and we get phi over mp to the p over 2. And then the slow roll equation for the evolution, 3h phi dot, that's, so it's convenient to use the relation we already found over here. Let's see, did we write it? Yes. So it's convenient to re-express phi dot in terms of d phi dn. So let's rewrite phi dot as h d phi dn. So then we get 3h squared d phi dn. Oh, and if you ever do things numerically, you'll find that n is a much nicer variable to work with than t because it's only changing by 60, whereas t could change by many orders of magnitude, and that's not convenient when you're doing things numerically. So this is minus v prime, which is minus lambda p m Planck cubed phi over mp to the p minus 1. And h squared, of course, is just coming from this. So if we put it, if we put that together, we get a very simple differential equation. d phi dn is some function of phi, and you can just integrate it. So I'll skip a step and write the result that n is equal to the integral. So minus the integral from whatever phi you're integrating to or integrating from until some phi sub e that denotes the end of inflation. So actually, this is the general formula. And now if we plug in for h squared and v prime, we find that this is just 1 over 2p m Planck squared, phi squared minus phi end squared. And then we can invert that and solve for phi as a function of n. But what is phi e that denotes the end of inflation? Well, that's where one of the slow roll parameters becomes large. And so let's write down the slow roll parameters. Their epsilon is p squared over 2 m Planck over phi squared. And eta is p times p minus 1 times the same thing, m Planck over phi squared. One thing you notice right away, we want those to be small during inflation. It means that phi has to be much bigger than the Planck scale. And so that's something that people criticize about chaotic inflation. You worry, do you really have good theoretical understanding of the model when you go above the Planck scale? But we have to just ignore that for the time being. And so if you look at those, you'll see that typically well, it's not so obvious, but for most cases of interest, this becomes bigger a little bit before this one does. So usually end of inflation is controlled by epsilon going to 1. And so that tells you that the end of inflation is at p over root 2 times m Planck. So now we can write something explicit for this. And then we can plug into our formula for the spectral index, which was some combination of epsilon and eta, and find that it's equal to, so ns minus 1 is minus p plus 2 m Planck over phi star squared. And so phi star, again, that's the value of phi when the reference scale k star, whatever one Planck wanted to use to measure when that crossed the horizon. So we need to figure out what's that correspondence. And to do that, then we have to go back to the formula for the number of, let's see, maybe I could do one more thing though. Since we have a relationship between phi and n, we can re-express this in terms of n. And so if you do that, you find that it's minus p plus 2 over 4p squared, 1 over n star plus p over 4 squared. Now n star is going to turn out to be of order 30, and p is going to be not too big. So usually you can just ignore the p over 4. But same problem now. We need to figure out what is n star, what's the appropriate value. And so for that, we need to go to the formula that I alluded to from Little and Leach 2003. And basically, it's just doing exactly what I did on that picture with the triangle, except doing it more carefully and taking into account what exactly goes on during a realistic reheating process. So it's too involved to go into the details here, and I'll just show you the result. So 67 minus log k star over a naught h naught. Okay, so that tells you how the choice of k star by the experimentalists will influence what number you put in here. But there's more. So there's 1/4 log v star squared. So scale of inflation at phi star. And then we need to know what was the energy density of inflation when it ended. So in my instantaneous approximation, these would be the same. Rho end would be equal to v star. And then you would, and then there's one other small correction that depends on the reheat temperature. Okay, so now if you plug in numbers, we can compute this for the value of k star that Planck uses, and that's just equal to 5.4. This one, we don't know how to compute yet because v goes as lambda, but so does rho, because rho is just v evaluated at a different scale. So this depends on lambda. So that means we need to figure out what is lambda, and we saw how to do that. It comes from matching the scale of the power spectrum, the normalization of the power spectrum. Now this one is always going to be a problem unless we add more to the model to tell us exactly how does reheating occur. Without that, T reheat is a free parameter. And so that's an uncertainty that is always difficult to eliminate. And what we'll see is that the usual choice is not to try to choose a specific value of T reheat, but just choose some reasonable range and see how it affects your prediction. But let's just, yes? Well, it's a bit historical, but Andre Linde's picture of the origin of inflation was that the universe started out in a so-called chaotic state, maybe a thermal state at the Planck scale with fluctuations and highly non-uniform, except if you just by accident had a little patch, a patch as big as the Hubble scale at the Planck scale, so a patch of size M Planck inverse that happened to be homogeneous enough, then inflation would start there, and then it would just take over, and you wouldn't care about all the inhomogeneities. So there's just that kind of picture of the origin, I think, that gives rise to this.
It has anything to do with the fact that it's a monomial?
No, I mean, that's just the simplest thing. You can do this same kind of thing with a polynomial or anything. That the main thing is that you just have to have, so the slow roll parameters go as v prime over v. So no matter what function you choose, typically if phi is big enough, v prime over v is going to be order 1 over phi. So in generic models, if you just take phi to be much bigger than the Planck scale, this should happen. So to fix lambda, remember, we just have to impose this requirement that v to the 3 halves over m prime v prime was 5 times 10 to the minus 4. And so you can just plug in our formulas, and then you find that lambda is 25 times 10 to the minus 8th from squaring that, p squared over 2p n star to the 1 plus p over 2. And what you notice from this is that regardless of, is this 30 or 15 or 60, this is a very small number. So that's another kind of general feature of chaotic inflation, that you need to put in some small dimensionless number to get the power the right level. Whereas the tensor to scalar ratio, so that's 16 epsilon, that's equal to 8p squared over 2p n star. Well, that's 4p over n star. And so if you put these things together, you can start to see where a tension would arise. So for instance, this is equal to 0.07p if n star is equal to 55, which turns out to be a kind of typical value. So you see now, if p is 2 even, just a massive scalar field, then we've already exceeded the upper bound from Planck. And in practice, what people do, rather than trying to carefully evaluate this formula, as I've been doing, they tend to just say, well, usually it's between 50 and 60 because of this uncertainty. And so that's the common practice. If you're doing this yourself, you might want to question that and try and plug in numbers and see if that's a very good thing to do. But nevertheless, this is what Planck and many authors do. And here we see the combined constraints in this plane on different models of chaotic inflation. So as we noted, p equals 2. it's already bad. Any higher p, much worse. And this is showing you the range of predictions as you go from 50 to 60 E foldings for n star. And as you lower p, then it starts to become more consistent with the data. P to the 2/3, that might sound weird, but there's a string theory inspired model called axion monodromy inflation, which can justify that fractional powers in general. Okay, so so chaotic models aren't the best fit, and let's talk a little bit more generally about what models Planck now prefers. And this is a big change from when I was. You might have noticed I'm a little bit rusty on inflation, so this has been quite challenging for me to lecture on. But so I did work on inflation about 10 years ago, and at that time, you could write down just about any model and get it to fit the data because you just had those two numbers, or three, n sub s and the amplitude, the normalization. So it's usually pretty easy to fit two numbers to whatever model you write down, and typically the tensor ratio was not a problem. Things have changed a lot because now there are just a relatively small handful of models that appear to be preferred by the Planck data, and they can be generally described as having a convex potential. Such as this model that's known as Hilltop Inflation, where you imagine you're starting inflation somewhere near the top of the hill. And so one typically just parameterizes inflation by taking a constant minus phi to some power. And of course, that wouldn't be a good parameterization forever because that would be unbounded from below. But you don't really care because inflation is going to end before you see these details. And so you could just imagine morphing this onto something that's doing something reasonable, but whose exact behavior you can't really probe with the CMB. So to write down the formula, Hilltop inflation would be some scale lambda to the fourth, 1 minus phi over some other scale to some power. And I'm leaving this as an exercise for you, if you care to, in the problem set that I wrote for inflation. You might have noticed there's a model down here labeled, which I've labeled R squared, that fits the data very well. It's interesting that this is probably the very first model of inflation ever proposed. It was by Starobinsky. In fact, it preceded Guth's paper. But the reason that Guth is known for inflation, not Starobinsky, is that while Starobinsky wrote down this model, he didn't realize all the implications that inflation has for solving the problems of the Big Bang. But I'll just write down this model, R squared inflation. And so it's just a model of gravity where, in addition to the Einstein-Hilbert contribution, you just put in R squared with some inverse powers of mass coefficient. And it turns out, it's at the end of my notes here, but we won't have time to get to them, that you can always put in an auxiliary field to re-express this in terms of a scalar field. So it's equivalent to ordinary scalar field potential of the form lambda to the fourth, 1 minus a negative exponential e to the minus root 2/3 phi over m Planck quantity squared. And so you see this is kind of like a hilltop model, but it's very flat on top. And so Planck seems to like that very much.
So that's not a dynamical.
I'm sorry?
You say that's an activity field, it's not a dynamical.
Well, it's really, it is dynamical because essentially what you've done when you make this replacement is when you add r squared to gravity, it adds an extra polarization to, it adds extra degrees of freedom, a scalar degree of freedom to gravity, which is not present in Einstein gravity. So this is just a nice way of expressing the dynamics of that extra degree of freedom, and it's absolutely equivalent at the level of the homogeneous background evolution. And then, yes?
The scale n, shall I think of that as like having a lower bound on Hubble, or it can be bigger than Hubble?
Let's see. I forget how big that scale m was supposed to be. It might be, see, at the very end of my notes, I explain how you do this. And so if you just go online, you'll see, but I don't remember what value m has to be in order to fit the data. And it looks like I didn't write it down. I think it might have to be a few orders of magnitude less than the Planck scale, actually. And then a model that you've no doubt or probably heard about is Higgs inflation, where you use the Higgs field itself as the inflaton. But you can't do that just in the standard model. The Higgs potential by itself is not flat enough. Or if you just tried to do chaotic inflation with the Higgs potential, the parameters would not be right at all. You know, lambda in the standard model is like 0.12, not 10 to the minus 8. But if you add an extra term coupling the Higgs field non-minimally to gravity, so we have the gravitational action, the standard model action, and if you add this non-minimal coupling of the Higgs field to the Ricci scalar, then this turns out to actually this turns out to have the same potential as r squared inflation. So it's kind of equivalent mathematically. And therefore it provides a very good fit. Boy, there was so much more I wanted to cover. I think I'm going to skip. I had a little thing in here about if you want to numerically solve the inflationary equation of the motion and not rely upon slow roll, but I'm going to skip that because I think a more important thing is to understand what's the origin of this quantum fluctuation of the inflaton. And it's pretty simple because it's just canonical quantization of a free scalar field, but instead of doing it in Minkowski space, you do it in de Sitter space. So remember the equation of motion for a scalar field in an expanding background, and we want to we want to solve it for a quantum field where we write the inflaton in terms of Fourier modes with coefficients that now become creation or annihilation operators. So this is creation and annihilation operators, just like in Minkowski space. And we're going to write these Fourier modes as e to the I k dot x. That's the spatial part. And in Minkowski space, we know what the time part would be minus I omega t. But now, because we're solving in an expanding background, we have to allow for some other t dependence. And so, well, this is also another exercise on my problem set, is just to work out what's the equation of motion. But I did most of it for you. The only thing that wasn't there was the part due to the gradient term in the Klein-Gordon equation. But anyway, if you plug in to the equation of motion, the Klein-Gordon equation, well, these two terms you recognize. This is just the Hubble damping term. And then we get the term from the potential. It's a free scalar field. It's a massive scalar field. So its potential is just a mass. And then the contribution from the gradient term is k squared, but it gets multiplied by e to the minus 2ht. And this you recognize, that's k over a squared. So this is the physical. That combination is just the physical k squared, whereas this k, that's the co-moving k, times fk equal to 0. So here I've just approximated the actual inflationary background as de Sitter space. Purely exponential expansion. And during inflation, so we want this to be the inflaton. And because of the slow roll parameters being small, so v double prime over v has to be small. That means that the mass of the field must be much less than h squared. And so it turns out that we're going to be able to ignore the mass. And remember, this is just k over a squared. And k over a is going to be greater than h before horizon crossing. Now, you can take that differential equation, and it's actually pretty simple. If you plug it into Mathematica, you'll just get Bessel functions. In fact, they're spherical Bessel functions, so we can express them in terms of trigonometric functions. And what you find is that the solutions are just a normalization constant. Oh, I'm sorry, I'm going to define a variable. Let's define a variable z, which is equal to k e to the minus ht over h. So that means z is less than 1 before horizon crossing, I think. Did I get that right? So k is large. No, k is large before horizon crossing. So
Crossing crossing into or out of?
It's always crossing out of when we say horizon crossing.
Wouldn't your decay be smaller than AH before it crosses?
Okay. See. K over A is getting smaller. Oh. No, but it's getting smaller, right? So at the moment, this is equal at the moment of horizon crossing. At later times, A is bigger. So this is less. Oh, it's less after horizon crossing, you're saying. No matter, let's just solve this thing. So it turns out it's J 3/2 plus IY 3/2 of Z. And, well, there's two linear combinations you can choose. And you'll see I've chosen this linear combination so that this will correspond to the usual Minkowski space solution when we go to very early times. So at very early times, K is becoming big. Physical K is becoming big compared to H. It means that the effect of H should be negligible, and we can think of it as being like Minkowski space. So this is C. In terms of elementary functions, sine Z over Z minus cosine Z minus I cosine Z over Z minus I sine Z, or C 2 over root pi Z. And then we get minus I over Z minus 1 e to the IZ. And now, in order to, we would like to find out what should we choose for this normalization constant. And here's my argument that we want to match onto Minkowski space for times much less than 1 over h, so that the physical k is much greater than h. Then the effect of the background shouldn't matter. And in that limit, we see that for very small times, we can expand the exponential, and then we get z is k over h minus kt approximately. And then you see that fk is equal to c square root of 2 over pi k over h e to the minus I kt. So there's our usual linear dependence on time, and the exponent like we would expect for free particle in Minkowski space. And in Minkowski space, I guess I can raise this a little bit. In Minkowski space, we know how to normalize this. So this looks like a normal canonical quantum field. It should just be equal to this. And so that tells us what to take for C. It's h over k square root of pi over 4k. I'll just take a few more minutes. So now if you plug this, we're interested in the fluctuations of this field. So the mean squared fluctuations of the field at a given point, and we can use the fact that, the usual thing that the vacuum expectation of a dagger k is a three-dimensional delta function of k minus k prime. So then we can just compute this, and it turns out to be integral d3k over 2 pi cubed fk squared. And so this is, so fk squared then is h squared over 2k cubed. And we get 1 plus k squared e to the minus 2ht over h squared. So that might look a little bit unfamiliar, but actually you can convince yourself that this part is exactly the usual contribution from flat Minkowski space. And so this one with the 1 is the new contribution coming from being in a de Sitter background. One thing you notice, the h's cancel out. So that's one clue that this is the flat space contribution. And another clue is that I can always rescale k by powers of e to the minus 2ht to make this look like integral d3k over the physical omega k. And that's exactly what you get. It's a divergent quantity that you get from Minkowski space. But this is the one that is scale invariant in the sense that we have integral d3k over k cubed. So we're getting equal power contributed by every logarithmic interval of k. And that's what we really mean by scale invariant spectrum. And it's going as h squared. And just the other, so this is a picture of these de Sitter modes. And it's showing that these modes are frozen. So let's see, these modes are frozen, should be after horizon crossing. So for z greater than 1, these modes are oscillating. For z less than 1, they're freezing out to some constant values. And that's illustrated by this picture where we can think of these modes as at early times they're oscillating and they're being stretched. At some point they reach the point where their wavelength is equal to the Hubble length, and that's this point z equals 1. And after that time they become frozen in time, and that's actually one of the things that is very useful for evolving these perturbations in time when you're doing cosmology. The fact that in between the horizon exit and crossing back into the horizon, those modes are frozen and basically not evolving. Well, there was a lot more I hoped to say, but I'm afraid it's just not time. So I'll leave it for you to look at my few pages of my notes if you're interested, but I'd like to start tomorrow on variogenesis. Yeah.
So I might have just missed this, but so at what point in the calculation can we see the freezing out of modes? If you take z greater than 1, is there a line?
It's just this picture that the exact behavior of the modes. It's just that they're oscillating at large z, and they're going to a constant as z goes to 0, and z goes to 0 is the limit of, so where is z defined? Oh yeah. So at large time, z's going to 0, that's all. Oh, and incidentally, so an exactly analogous calculation holds for gravity waves, and so that's why their amplitude, their quantum fluctuations are also of order h. Okay, so I guess we're ready for coffee.